Good, we have a target to shoot for. Let's write out the problem for number 39 and then start filling in the gaps and use that as kind of the methodology here. So the problem is, it uses a lot of words I haven't used in class yet. So for this function, for what is the function there? Y or f of x equals 1 minus x squared. It says find the formula for the Riemann sum obtained by subdividing the given interval into n equal subintervals. So it says Riemann sum, whatever that is, subdividing something into n equal subintervals. And the thing we're going to subdivide is the interval from 0 to 1. And using the right-hand endpoints for rectangle heights. And then take a limit as the number of pieces goes to infinity. So we have to go in and fill in what a couple of these things actually mean. And then we'll go through and compute one of these sums and see that we can actually find the exact area there. So here's the idea of Riemann sums in a nutshell. It's looking at exactly what we did last time. We've got some graph, y equals f of x, and we've got some interval from A to B. Okay, so we're only interested in the graph on actually between A and B. Now, the idea, there's some terminology that comes up. A partition is a list of numbers that look like this. The first number is x0, and that's less than x1, which is less than x2, which is less than, in general, less than x of k minus 1, less than x of k, x of n minus 1, which is less than xn, which is equal to b. So I can draw that graphically on here by saying x0 is always your left-hand endpoint, and then there's some point x1, and then there's some point x2, and some point x3, and x4. Out here is x of k minus 1, just a typical interval. Here's x of k. The next to last point is x of n minus 1. And then the right-hand endpoint is point number n. I put no restriction here. I've not said the points have to be equally spaced. Basically, you can do it any way you want. With that partition, we can throw in some terminology. So this is the kth subinterval. So this one, between x0 and x1, that's the first subinterval of the partition. And then we have the second subinterval, the third subinterval. The subinterval number is actually just, you can just count the right-hand endpoint. Interval number 1, that's the right-hand endpoint of x1. This last one is the nth subinterval of the partition. Okay. The width of a subinterval width is something called delta x of k. It's the change in x of k. And what that is it's the difference of the right-hand endpoint xk minus the left-hand endpoint. So what you find is that delta x1 is just x1 minus x0. It's just the length of that interval. And delta x2 is just x2 minus x1, and so on. So you need the widths of the subintervals because you want to talk about rectangle areas. And to talk about areas, you need a notation for the width and a notation for the height. Once you've got a partition, we want to have some scheme for going through in each of these subintervals and picking a particular point. Now, we've looked at the special case of right-hand endpoints. But you could take the midpoint of every subinterval, or you could take the left-hand endpoint, or you could take a random point on each subinterval. So in the notation in the book, they're going to introduce this, that you've got some point C1 in the first interval, and some point C2 in the second interval, some point C3 in the third interval, C4 is some point in the fourth interval. Over here is some point C sub k. The last one would have C sub n. And the purpose those are going to serve is we're going to go up here to the point C1, f of C1, to get our height. So basically you plug in the C value into your function to get the height of a rectangle, and then you use that to build your first rectangle. And then at C2 you go up to the curve, so you have the point C2 and f of C2. F of C2 is the height, the red segment that I drawn. And if you go to the left and right of that, you'll get that rectangle. Over here at rectangle number K, you've got this point somewhere on the interval that gives you the height, CK and f of CK. And then the right-hand endpoint over here at the left-hand endpoint, you'll get this rectangle. And so as you do this, you eventually get a height for every rectangle. The last one, of course, is going to go to C sub n, go up and get the height, and then we'll just move it to the right and to the left. And so we're approximating the area under the curve by building all these rectangles and looking for the areas in those, and we're going to add them up. And so to add them up, what we'll get is the sum k going from 1 up to n, because that's how many rectangles we have. And for each of these, we have f evaluated at c sub k times the width, delta x sub k. So the way this breaks down, this is the height, this is the width. If we do that, starting at k equals 1, that's going to give me delta x1 times f of c1. And then delta x2 times f of c2. It's just going to give me the area of each of these rectangles for each value of k going from 1 to n. This is called a Riemann sum for the area under f of x on the interval from a to b, or just the Riemann sum of the function f on the interval from a to b. Right? It says, for that function, find a Riemann sum gotten by subdividing into n equal subintervals this interval for whatever endpoints they give us. In this case, they tell us a is 0 and b is 1. And then we want to use the right-hand endpoints. Okay, so what this says is that c sub k is equal to x sub k. That's what it means to use the right-hand endpoints. The right-hand interval of each endpoint is just the x with that subscript on it. So if we go back over here, that would just have that point C1 being at x1, and C2 being at x2, and C3 being at x3, all the way down the line. So it's one way of doing it. In this problem, they also have us dealing with equal subintervals. Instead of allowing those widths to all be different, we're going to insist that we want them all to be the same. So when we talk about this idea of a Riemann sum, it's not enough to talk about dividing it up into n pieces and letting n go to infinity. We also have to build in the idea that the size of the largest width rectangle goes to 0. So if we look back at this problem, let's take a look at what this has to become. We need evenly spaced intervals between 0 and 1. If we take the interval from 0 to 1, here's what 1 minus x squared looks like. The curve starts out at a height of 1 and it drops down at 1, it has a height of 0. And if we're making n equal pieces, how wide is the first piece? So it's the width of the piece if we take n as the number of pieces. So in general, if there are n equal pieces, then 1 over n is going to be the width. And so this partition looks like this first point is at 1 over n, the next point is at 2 over n, the next point is at 3 over n, this next to last one is at n minus 1 over n, and then the last point is 1, which is equal to n over n. And so that tells me where my rectangles are going to be. If we take rectangle number k, that would be k minus 1 over n up to k over n. We're supposed to use the right-hand endpoint. So the y value here, this is k over n for the x value, and 1 minus the x value squared for the height. And so the area of this rectangle number k is c sub k times delta xk. But delta xk, we just said that the width of each interval is 1 over n. And this is f of x sub k, because we said that in each interval we take the right-hand endpoint. And so that's 1 minus k over n, the value of the right-hand endpoint squared. And so the sum we want to look at is the sum, k going from 1 up to n, of the quantity 1 minus k over n squared all times 1 over n.